We all have psychological blind spots, stuff we're either completely unaware of or just choose to ignore. This can include tendencies like only looking for opinions that back up what we already believe, or even personality traits we'd rather not deal with. But to tackle huge problems like climate change, we really need to face these blind spots head-on. In her book, Miseducation, How Climate Change is Taught, Katie Worth uncovers how American schools are really dropping the ball when it comes to teaching about climate change. She found that what students learn is often full of wrong information, swayed by politics, and lacking strong science. This frequently leads to minimizing how serious climate change is and ignoring the fact that humans are causing it. Basically, miseducation shows that kids aren't getting the solid, science-based education about climate change they truly need. This seriously impacts their understanding of the issue and their ability to actually help in a world that's rapidly changing. Everyone knows that professional basketball teams look for the most skilled and focused players to win championships. But what if an excessive focus on one area could actually make a team less capable of winning? I raise this question because I see a similar issue in education. While diversity, equity, and inclusion initiatives have their place, perhaps they are drawing too much attention away from core subjects like science, technology, engineering, and math. For example, surveys show that many students struggle with even basic science concepts. This leads me to believe that a major reason for this struggle is that teachers themselves aren't receiving sufficient training in these subjects. It's difficult to teach something effectively if you haven't fully mastered it. You know the saying, if all you have is a hammer, everything looks like a nail? That's essentially Maslow's hammer in action. It describes the tendency to over-rely on familiar tools, even when they're not the best solution for the problem at hand. Consider, for example, how many educators prioritize diversity, equity, and inclusion lessons over science, technology, engineering, and math education. This isn't necessarily due to a lack of regard for STEM. Instead, it results from the fact that their training and professional development have heavily emphasized DEI. If DEI is the hammer they've been given, they'll naturally use it to address classroom issues and curriculum. Put another way, a form of miseducation is happening because teachers feel more confident discussing social justice topics, whereas the benefits of robust STEM learning often seem more distant and abstract. When the Soviet Union launched Sputnik in October 1957, it sent shockwaves across the United States, sparking a national crisis of confidence in American technological and educational superiority. This Sputnik shock made Americans question if their tech and education were still the best. Because of this, the U.S. quickly shifted its focus, pouring a ton of energy and money into science, technology, engineering, and mathematics education. Basically, science and engineering became super important for national security, leading to a huge push to create more scientists and engineers. Fast forward to today, even though scientists have been warning us about human-caused climate change for decades, it seems like the American education system hasn't caught up. Surveys show that a huge chunk of kindergarten through 12th grade teachers, about 76%, have never gotten any training on climate change or how to teach it. And while most teachers and school leaders agree that teaching about climate change is important, a whopping 80% feel like they aren't properly prepared to do so. It makes you wonder why we're not seeing the same urgent, national focus on climate education as we did with STEM after Sputnik, especially since climate change is such a massive threat. Since there's a massive chasm in understanding science, let's kick off our look into climate change with a neat experiment. A candle and rising water. This simple demo uses basic scientific ideas to help us grasp a much bigger concept. The setup. Imagine this. You have a shallow dish or bowl with a bit of water in it. Place a lit candle right in the middle. Now, carefully put a glass jar or cup upside down over the burning candle, making sure the open edge of the jar is underneath the water. Watch what happens. The candle flame will shrink and then go out. The water level inside the jar will rise quite a bit. The water level outside the jar will drop a little. The experiment where you put a glass over a burning candle and the water rises might seem basic, but it actually shows some key science stuff about how candles burn and how that affects the air inside the jar. So, when a candle burns, it's called combustion. Basically, the candle wax, which is made of stuff called hydrocarbons, reacts with the oxygen in the air. This reaction creates carbon dioxide and water vapor, plus heat and light. Now, you can think of this little experiment as a super simplified version of what's happening with man-made climate change. Just like the burning candle makes carbon dioxide, when we burn huge amounts of fossil fuels like coal, oil, and natural gas for energy, we release tons of carbon dioxide into Earth's atmosphere. The big difference is that in the candle experiment, the water rises mostly because the air inside cools down and the pressure drops. But in Earth's atmosphere, the extra carbon dioxide acts like a greenhouse gas. This means it traps heat that would normally escape into space, which is what's causing our planet to warm up. You can kind of imagine Earth's atmosphere like that sealed jar. When we keep adding a lot of heat-trapping gases like carbon dioxide, it messes with the whole system's energy balance, leading to long-term changes in our climate. The next scientific idea to grasp is that when you burn just 1 gallon of gasoline, it releases about 20 pounds of carbon dioxide. Think of the gasoline in your car as mostly made up of tiny carbon and hydrogen atoms. When that gasoline burns in your engine, these atoms don't just vanish. Instead, they link up with oxygen that's in the air around us. Picture the carbon atoms in the gasoline like little marbles. During the burning process, each carbon marble grabs 2 oxygen atoms from the air, which are like slightly heavier marbles. These 3 marbles, 1 carbon and 2 oxygen, then form a new molecule, carbon dioxide. Now, here's why the weight goes up so much. The carbon dioxide molecule doesn't just weigh what the original carbon weighed. It's the combined weight of that carbon plus the 2 oxygen atoms now attached to it. Oxygen, at this atomic level, is actually quite a bit heavier than you might expect. So, even though the carbon in a gallon of gasoline only weighs a few pounds, when each carbon atom teams up with 2 oxygen atoms from the air to create carbon dioxide, the resulting carbon dioxide molecule ends up being much heavier than just the initial carbon by itself, roughly 3.7 times heavier, in fact. That's why, when you burn that relatively light gallon of gasoline, the carbon inside it pulls in a significant amount of heavier oxygen from the air. The resulting carbon dioxide gas released into the atmosphere then weighs considerably more, about 20 pounds. It's almost like a small amount of something light transforming into a larger, heavier substance by combining with its surroundings. The air, which seems weightless, actually adds a substantial amount of mass to the carbon dioxide that's produced. You unlock this door with the key of imagination. Beyond it is another dimension, a dimension of sound, a dimension of sight, a dimension of mind. You're moving into a land of both shadow and substance, of things and ideas. You've just crossed over into the Twilight Zone. I've quoted the opening monologue of that TV show because, just like those mysterious, often invisible forces that plague the characters in the Twilight Zone, the primary drivers of climate change, greenhouse gases, are invisible to the naked eye. To give you some perspective on these gases, like carbon dioxide, imagine that a standard barrel of oil is 42 gallons, and roughly half of that barrel becomes gasoline when refined. Looking at the last 2 decades, global oil consumption has jumped from around 84 to 86 million barrels per day in the mid-2000s, to projections of 100 to 105 million barrels daily by 2025. This massive amount of fossil fuels being burned every single day raises a huge question. Is there a global impact from burning millions of barrels of oil daily that can be scientifically measured? The Keeling curve is a famous graph in climate science that shows how much carbon dioxide has been in Earth's atmosphere based on measurements from an observatory in Hawaii. Started by scientist Charles David Keeling, this curve reveals 2 key things. First, a yearly zigzag pattern where carbon dioxide levels drop in spring and summer as northern hemisphere plants grow and absorb it, then rise and fall in winter as plants decay. And second, a clear, ongoing upward trend in carbon dioxide levels every single year. This consistent rise in atmospheric carbon dioxide directly links to human activities like burning fossil fuels and deforestation, providing undeniable, long-term proof of our impact on the planet. Ever wonder how plants grow and get their energy? The answer is related to carbon dioxide in the atmosphere. Well, imagine a plant as a tiny factory that uses sunlight to whip up its own food. This amazing process is called photosynthesis. Essentially, plants take carbon dioxide from the air and water from the soil, then use sunlight to turn these simple ingredients into sugars, their food, and oxygen, which they release back into the air for us to breathe. Here's a quick breakdown. The plant's leaves have tiny pores that suck in carbon dioxide, while its roots pull up water. Inside the leaves are special compartments called chloroplasts, which are packed with chlorophyll, the green stuff that acts like a solar panel, capturing sunlight. With this energy, the plant transforms the carbon dioxide and water into glucose, its main energy source. This whole photosynthesis thing is super important, especially when we talk about climate change. Trees and other plants are like natural vacuum cleaners for the atmosphere. When a tree does photosynthesis, it sucks in carbon dioxide and uses that carbon to build its leaves, branches, and trunk. This act of storing carbon in its body is called carbon sequestration. How much carbon a tree can hold depends on a few things. The type of tree, its age and size. Younger, faster-growing trees actually take in more carbon per year, and even where it's growing. On average, a mature tree can gobble up somewhere between 10 to 40 kilograms. That's about 22 to 88 pounds of carbon dioxide annually. So, trees and forests are vital in helping us fight climate change because they act as natural carbon sinks, reducing the amount of greenhouse gases in our atmosphere that contribute to global warming. Learning the science behind human-caused climate change can feel a lot like stepping into an episode of The Twilight Zone. That's because everyday life rarely exposes individuals to surprising scientific facts. For instance, did you know it took 98 tons of ancient plant material and millions of years to create just 1 gallon of gasoline? This really highlights how much buried sunshine, the energy fossil fuels hold, originally captured from the sun by plants, was needed to produce even a small amount of fuel. The sheer scale of time and space involved in climate change, along with its invisible but powerful forces and unsettling implications for the world, can truly yank individuals out of their normal routine and into something that feels oddly unfamiliar and even a bit scary, much like that classic show. You know how you can't see carbon dioxide, even though it's a big deal in climate change? Well, the same goes for infrared radiation, another invisible player in our climate story. Back in 1800, a scientist named William Herschel did a super cool experiment to find this invisible light that we now call infrared radiation. He knew it was there because he could feel its heat, even if he couldn't see it. Here's how he did it. Herschel shone sunlight through a glass prism, which, just like a rainbow, split the white light into all its different colors: violet, blue, green, yellow, orange, and red. He then took 3 thermometers with black painted bulbs. Black is good at soaking up heat, and placed one in each color of the spectrum, checking the temperature. He also put 2 control thermometers outside the visible light spectrum to make sure his readings were accurate. As he moved the thermometer from violet towards the red end of the spectrum, he noticed the temperature kept going up. But here's where it got really interesting. He decided to place a thermometer just past the red light, in a spot where there was no visible light at all. To his surprise, that thermometer showed an even higher temperature than the red light itself. This made him realize there had to be some kind of invisible, radiant heat beyond what our eyes can see. He figured that if different colors of visible light had different heating powers, then there must be other types of light, totally invisible to us, that also carry heat. And he was right. William Herschel's super simple experiment was a huge deal for science. It totally flipped what scientists thought light was. He realized there was energy beyond what our eyes could see, hinting that the universe is full of stuff and energy we can't detect with just our senses. This was a major game changer, pushing scientists to look past the obvious and invent new tools to explore the invisible. It turns out, the electromagnetic spectrum is the whole range of all types of electromagnetic radiation. Think of radiation as just energy that travels and spreads out in waves. It's like a giant rainbow that includes not just the visible light we see every day, but also a ton of other types of light that are invisible to us. All of this electromagnetic radiation travels in waves and carries energy. These waves have a few key characteristics. Wavelength. This is simply the distance from one peak of a wave to the next peak. Frequency. This tells you how many wave cycles pass a certain point every second, and it's measured in hertz. Energy. This is the amount of energy a single particle of electromagnetic radiation, called a photon, carries. These 3 things are all connected. If a wave has a shorter wavelength, it'll have a higher frequency and more energy, and vice versa. And get this, all electromagnetic waves travel at the speed of light in a vacuum. You know how when you get in a car on a sunny day, it gets really hot inside, even if it's cool outside? That's kind of like the greenhouse effect, but for the whole Earth. Basically, the sun sends out energy, and some of that energy gets absorbed by the Earth's land and oceans, making them warm up. Then, the warm Earth sends some of that heat back out as infrared radiation, a type of invisible light that was discovered by Herschel's super simple experiment that we feel as heat. That's where greenhouse gases, like carbon dioxide and methane, come in. These gases in our atmosphere act like a blanket, trapping some of that outgoing heat and sending it back down to Earth. This natural process is super important because without it, Earth would be a frozen planet, way too cold for us to live on. Now, if you look at the moon, it's about the same distance from the sun as Earth, but it gets super hot during the day and freezing cold at night. That's because the moon barely has an atmosphere. Its gravity isn't strong enough to hold on to gases, so there are hardly any greenhouse gases to trap heat. So, while Earth's atmosphere keeps us cozy, the moon's lack of one means all the heat it absorbs during its long day just escapes back into space during its equally long night, leading to those wild temperature swings. It just goes to show how important our atmosphere and those greenhouse gases are for keeping Earth's temperature just right for life. To understand climate change, you need to examine Earth's energy budget. Imagine the planet as a bathtub where the water level represents global temperature. The stable state, equilibrium, if the water entering from the faucet, sunlight, equals the water leaving through the drain, heat escaping into space, the water level stays the same. In this state, the temperature of the tub remains steady. The greenhouse effect. This acts like the drain system, naturally regulating how fast the water leaves. A natural greenhouse effect means the drain is perfectly sized to retain enough warmth in the tub, preventing Earth from freezing. Radiative forcing. The push. This measures the imbalance between the faucet and the drain. If you clog the drain by adding greenhouse gases or turn up the faucet, increasing solar intensity, you create a positive forcing that causes the water level to rise. Trapping energy. Car metaphor. Think of the greenhouse effect like a car with the windows rolled up. Sunlight can enter, but the heat gets trapped inside. Radiative forcing represents the imbalance in energy. For example, if the sun gets brighter or you paint the car black, you increase the force of the heat, making the internal temperature rise faster because energy is entering more quickly than it can escape. This wraps up the first part of what students and teachers should understand about key ideas of climate science. In the second part, I'll explain that Earth has seasons mainly because its axis is tilted about 23.5 degrees as it orbits the sun. This tilt means different parts of our planet get more direct sunlight at different times of the year. After that, we'll dive into something called Milankovitch cycles. These are long-term changes in Earth's orbit and tilt that affect how intense our seasons are over super long periods. While the tilt is what gives us our yearly seasons, these much slower changes in the tilt, along with shifts in Earth's orbit and wobble, are actually key players in long-term climate changes, like when ice ages come and go. By the end of this second part, you'll have all the information you need to confidently understand why scientists are so sure that humans are causing the current climate change.